In this lesson, we're going to talk about thin lenses. Now, thin lenses, we've looked at two varieties. We've looked at converging lenses and diverging lenses, and they're called that because of the way they focus light. On a converging lens, the light focuses to a point, but what's cool about lenses is they transmit light. So a converging lens actually has two focal points, and if we think about parallel rays of light coming in this way, they would all focus to this point. And in fact, we could tilt those rays of light so they came in this way, and they would focus on a plane that goes through the focal point. And just like when we had mirrors that had focal lengths, we have a focal length for an axis, or for her lens. But we measure it from this axis, not from the surface of the lens, because the light gets refracted twice, and for thin lenses, measuring from the axis is good enough. Now, I said two focal points because if light was going the other way, it would focus from that point. And we know how to draw ray diagrams with this converging lens. We would have our lens, and we put a focal point here and a focal point here, and depending on where we place our object, we're going to get different types of images, but the three rays we draw are always the same. One ray to the lens, and we go to this axis, and then it bends through the focal point. And our second one through the first focal point, to the lens, and then it bends as though it had come from a parallel axis, because if light was going the other way, it would bend through that focal point. And so my principal axis is here, so I can see my image is going to form right there. It's going to be inverted, it's going to be magnified, it's going to be real. Now the third ray is right through the lens, it goes through unchanged, and so I did a poor job of drawing my rays. They should all come together at a point. Now, a diverging lens, or a concave lens, is similar, except that it diverges the light instead of focusing it to a point. So it also has two focal points, and the light that comes into this one gets bent as though it had come from that focal point. So when parallel rays of light come in, they diverge from each other. Now that makes this lens incapable of producing a real image. It cannot focus light to a point, so it can't project an image. But we can still see virtual images. And again, the ray diagram is similar. Focal point, we put our object out here. I can draw the light here. It bends this way as though it had come from that focal point. This one, I'm going to take it towards that focal point, and it will bend parallel. So then the virtual ray comes back, and then the third point is right through the lens, and we see those produce an image there, and that image is upright, it's reduced, and it is virtual. Those rays aren't actually coming from there, they're coming from back here. They don't come to a point. It's a virtual image. Now, when we're looking at converging lenses, we have to realize that they have a positive focal length, and diverging lenses have a negative focal length. And that's important when we use the thin lens equation, which says 1 over the image distance plus 1 over the object distance, whoops, it's a 1 over an object distance, is equal to 1 over the focal length. For a converging lens, the focal length is positive. For a diverging lens, the focal length is negative. Now, as far as image and object distances go, object distance is positive if the object is on the same side as the light is coming from. So if the light is coming from the left side of the mirror, or the lens, sorry, then the distance is positive if the object distance is on the left side. Image distance is positive if it's on the opposite side from which the light emanates. So this would be a positive image distance. This would be a negative image distance. This would be a positive image distance and a positive object distance. Now, we generally only see positive object distances, but we don't have to when we get into combinations of lenses, when the image of one lens can actually be the object for the second lens. But the thin lens equation still holds in that case. You just have to pay attention to signs. Now, speaking of, there's magnification. Just like with mirrors, we get magnification. And this tells us how much the image is compared to the object. So we could say negative di over do, and that's because for a positive magnification, the image should be upright. If it's greater than 1, the image is bigger than the object. So the sign convention helps us know that. It's also equal to image height divided by object height. So sign convention there is necessary so you know if your image is upright or inverted. Now, there's one other thing to mention, and that's power. power of a lens is equal to 1 over the focal length of the lens. We haven't talked a lot about that. Ophthalmologists, optometrists use that when describing lenses. It is measured in this unit called a diopter, and a diopter has a symbol D, but it's really just an inverse meter. So if you see a question about the power of a lens, power is 1 over focal length.